Hello, this is Dr. V.C. Sontake, Assistant Professor in the Department of Mechanical Engineering, St. Vincent Pallotti College of Engineering and Technology, Nagpur. I am going to teach the course Heat Transfer. These are the objectives of this video lecture. Objective 1 is to explain electrical analogy of heat transfer. Objective 2 is to define thermal resistance and thermal conductance and their significance with regard to heat transfer. And objective 3 is to differentiate thermal conductivity and thermal conductance. So let us start with the heat transfer and its electrical analogy. Electrical analogy of heat transfer. There seems to be an analogy between electricity transfer and heat transfer. Let us consider an electrical conductor. A voltage difference delta V has been applied across its two faces. By virtue of this voltage difference, a current I will be flowing through it. And let us say Re is the electrical resistance of the material of this electrical conductor. Keeping in mind the same phenomena, let us consider a thermal conductor having delta T temperature difference has been maintained across its left and right faces. Now, by virtue of this temperature difference, heat transfer will take place from left to right face at some rate. Now, in case of thermal conductor, delta T temperature difference corresponds to voltage difference in electrical heat transfer. This heat transfer rate corresponds to current flow. And since there is an electrical resistance of the electrical conductor, so keeping in mind this electrical analogy, we must expect a resistance of the material of this thermal conductor offered to the path of the heat flow. And this thermal resistance is nothing but thermal resistance. Now let us compare one by one electrical energy transfer and heat energy transfer and try to deduce some important conclusions out of it. So first parameter is flow quantity. In case of electrical transfer, it will be charge in coulomb, and in case of heat transfer, it will be heat energy in joule. The driving potential will be voltage difference in volt and temperature difference in degrees Celsius in heat transfer. The flow quantity or the flow rate will be current, which is nothing but charge flowing per unit time in ampere in case of electrical transfer, and heat transfer rate will be amount of heat flowing per unit time in watt in case of heat transfer. Similarly, resistance to flow. There will be electrical resistance of the material of the electrical conductor given by Re is equal to delta V by I in ohm. And as we are saying, there exists an electrical analogy between heat transfer phenomena. So we expect a thermal resistance represented by RTH. Its unit yet to be found out. Now from Ohm's law, the current is equal to delta V by Re. In case of electrical energy transfer, current is the flow quantity delta V is the driving potential, and Re is the resistance. So let us represent this term in a most generalized form. Flow quantity is equal to driving potential over resistance. Now let us extend this relationship between these three variables to heat transfer phenomena. In case of heat transfer, Q is the flow quantity, delta T is the driving potential, and there exists a resistance RT called as thermal resistance. So what is my point of contention? From the electrical analogy of heat transfer, we found out first this relationship between Q, delta T and thermal resistance, and we have defined a new term called as thermal resistance. So if I am considering the heat transfer across this thermal conductor by virtue of the temperature difference delta T, from the concept of electrical analogy, I can represent the entire heat transfer phenomena in the form of electrical circuit given by this diagram, and this is called as equivalent electrical circuit of heat transfer phenomena. Whereas this temperature difference between T1 and T2 corresponds to voltage difference in electrical energy transfer. Flow of this heat transfer is corresponding to current flow in electrical transfer. So this RT will represent resistance to the path of this heat flow called as thermal resistance. So we can represent this electric heat transfer phenomena by this equivalent electrical circuit. So whenever we are going to study the heat transfer phenomena, we will be drawing this equivalent electrical circuit. As we have discussed from the previous slide, we have got this relationship between Q, delta T and RT. Let us rewrite this equation for RT thermal resistance as RT is equal to delta T over Q. So this is a very important relationship. This equation we are going to use extensively while solving the problems. Now since RT is a term, it will have a unit. Let us try to find out the unit of this thermal resistance. So if I take the unit of temperature difference in Kelvin and unit of heat transfer rate in watt, the unit will be Kelvin per watt. I can also represent the unit of RT as degrees Celsius per watt. Now thermal resistances in various modes of heat transfer. As we know, there are three different modes of heat transfer: conduction, convection and radiation. We also know all these three modes are governed by three different laws of heat transfer: Fourier's law of heat conduction, Newton's law of cooling and Stephen-Boltzmann law of radiation. And all these three laws give equation of heat transfer rate. And these three equations are different. Just now we have seen there exists a relationship between thermal resistance, temperature difference and heat transfer rate. So the moment mode of heat transfer changes, the moment type of medium changes, equation for heat transfer rate will also change, and accordingly different expressions for thermal resistances can be deduced for that particular mode of heat transfer. So let us try to deduce different expressions for thermal resistances in various modes of heat transfer. Let us first consider heat transfer by conduction mode. So we will try to find out thermal resistance in conduction mode, also called as conductive thermal resistance. In order to do so, let us consider a thermal conductor where heat transfer rate is taking place by virtue of temperature difference from left phase to right phase. For the sake of example, I am considering T1 is greater than T2, and this is its equivalent electrical circuit. So Q is the flow quantity, delta T is the temperature difference. So there must exist a resistance offered to the path of the heat flow from the concept of electrical analogy. And since it is conduction mode of heat transfer, it will be called as a conductive thermal resistance. From Fourier's law of heat conduction, the rate of heat transfer is given by equation Q is equal to Ka into delta T by L, where L is thickness of the material. Here I have represented this as a delta X in this diagram. It is also called as length of path of heat flow. If I rearrange this equation, Q is equal to delta T over L upon Ka, and compare with the standard form of Q is equal to delta T over RT, this will give me conductive thermal resistance RT conduction given by L over Ka Kelvin per watt. So whenever heat transfer rate is taking place by conduction mode through a solid medium by virtue of temperature difference, this much will be the resistance offered by the material to the path of the heat flow, and it is called as conductive thermal resistance, and it is calculated as L over Ka Kelvin per watt. Similarly, let us consider heat transfer by convection mode. So thermal resistance in convection mode, it is also called as convective thermal resistance. To do so, let us consider heat transfer from this solid surface to the fluid medium. Let's say the solid surface is at temperature Ts and the fluid is at temperature T infinity. For the sake of expression, I am considering Ts is greater than T infinity. Heat transfer will take place from the surface to the fluid by convection. And this is its equivalent electrical circuit. In this case, this thermal resistance will be called as a convective thermal resistance. Now from Newton's law of cooling, the heat transfer rate is given by the equation Q is equal to HA delta T. Rearrangement of this equation Q is equal to delta T over 1 upon HA, and comparison with the standard form Q is equal to delta T over RT will give me convective thermal resistance RT convection is equal to 1 over HA Kelvin per watt, where H is called as convective heat transfer coefficient and its unit we have already discussed, watt per meter square Kelvin or watt per meter square degree Celsius. So whenever heat transfer takes place from surface to the fluid by convection mechanism, this much resistance will be offered by this fluid material to the path of the heat flow. Mind well, 1 upon HA is the resistance offered by the fluid to the path of the heat flow whenever heat transfer is taking place by convection. Now here consider heat transfer rate by combined mode of heat transfer. From this phase to this phase, obviously by conduction, and from surface of the body to the fluid surface by convection. So what will be the total resistance of this phenomena? When heat transfer takes place from phase 1 to the phase 2, it will be by conduction. So material of this body will offer resistance to the path of the heat flow, and it is called as conductive resistance and given by L over Ka. Similarly, when heat transfer takes place from this phase 2 to the fluid surface, it will be by convection, and this fluid will offer resistance to the path of the heat transfer. It is called as convective resistance given by 1 over 1 upon HA Kelvin per watt. So if I consider the total resistance offered to the path of the heat transfer as a whole, considering conduction and convection mechanism, this will be the total thermal resistance. This is very important conclusion from this discussion. Now let us move on to the radiation mode of heat transfer. Thermal resistance in radiation mode. It is also called as radiative thermal resistance. To deduce the expression for radiative thermal resistance, let us consider a body at a surface temperature T1 completely surrounded by another body at surface temperature T2. Once again, for the sake of explanation, I am considering T1 is greater than T2. So heat transfer by radiation will take place by convection from body 1 to the body 2. From Stephen-Boltzmann law of radiative heat transfer between these two bodies can be given by the expression Q is equal to sigma A1 epsilon 1 into T1 power 4 minus T2 power 4, where this epsilon is called as emissivity, okay, and let us compare this expression with the standard equation Q is equal to delta T over R. Let us first try to simplify this. In order to simplify, we have to simplify this term first, T1 power 4 minus T2 power 4. Also, this equation is not in the standard form, that is temperature difference over thermal resistance. So T1 power 4 minus T2 power 4 can be simplified as T1 square minus T2 square into T1 square plus T2 square. This comes from the very fact, this formula. In mathematics, we have come across this formula. Further, T1 square minus T2 square can be represented as T1 minus T2 into T1 plus T2. So after simplification, the heat transfer rate equation by radiation becomes sigma A1 epsilon 1 T1 minus T2 into T1 plus T2 into T1 square plus T2 square. Now let us rearrange this heat transfer rate equation in this standard form. So it will give me Q is equal to T1 minus T2, that is temperature difference, over this entire quantity. Now when I compare this equation with the standard equation, I will have expression for radiative thermal resistance given by 1 over sigma A1 epsilon into T1 plus T2 into T1 square plus T2 square. So whenever heat transfer is taking place from this body 1 to the body 2 by radiation, let's say some medium is present, so that medium will offer this much thermal resistance to the path of the radiative heat transfer. So this way we have deduced the different expressions for thermal resistance in conduction mode, convection mode and radiation mode. Now let us define a new property called as thermal conductance. Thermal conductance is the reciprocal of thermal resistance of the system. It is represented by C suffix T. So mathematically, thermal conductance is nothing but 1 upon thermal resistance. So since we have different expressions of thermal resistance in conduction, convection and radiation mode, so we can also get different expressions of thermal conductance in all these 3 modes of heat transfer. And unit of thermal conductance will be watt per Kelvin or watt per degree Celsius. Now here we have defined one property, thermal conductance. We have also defined one property of the material called as thermal conductivity. Now from their name, both sound same, but there is a big difference. There is a too much difference between thermal conductance and thermal conductivity as far as heat transfer phenomena is concerned. So let us try to find out the difference between thermal conductivity K and thermal conductance Ct 1 by 1. Thermal conductivity is the property of the material or medium, whereas thermal conductivity is not the property of material or medium. Rather, it is property of the system. It is constant for material or medium. Thermal conductance is not constant for material or medium. It varies with the area normal to heat transfer, temperature difference and prevailing conditions. The unit of thermal conductivity is watt per meter Kelvin, whereas unit of thermal conductance is watt per Kelvin. Now, in order to understand the fourth difference, let us consider 4 different shapes and of different sizes, but they are made up of same material, let's say copper. So for all these different shapes of different sizes, if I consider them made up of the same material copper, their thermal conductivity will be same. But the thermal conductance value, although I am considering all these shapes of different sizes are made up of the same material, but thermal conductance value will be different. It will be different for this, different for this, different for this, and different for this cylindrical shape, though they are made up of the same material, copper, for example. So this is something very important difference you must keep in mind between thermal conductivity and thermal conductance. So with this, I come to an end of this video lecture. These are the learning outcomes. After going through this video lecture, you will be able to explain electrical analogy of heat transfer phenomena. And based upon this electrical analogy, you will be able to define thermal resistance and thermal conductance. And you will be able to derive expressions for thermal resistance in various modes of heat transfer. And finally, you will be able to differentiate thermal conductivity and thermal conductance. With this, I come to an end of this video lecture. Thank you for passionate listening. Happy learning.